Well, hello, my theosophical buddies. This is Jeff Curtis coming to you again from the Sierra foothills, up where I live near a little town at about 3,000 feet. And I'm glad that some of you are with me tonight or might be viewing this video later in the future with the magic of YouTube, which is fun. I'm going to see if I can get this screen glare out of my glasses. Well, maybe if I just do this, it's not quite as bad. Um, what I want to do tonight is to just move the ball a little further down the field, talking about some of the operational, scientific, philosophical implications of what we've learned over the last 100 odd years applying the science of quantum mechanics and trying to understand how reality works at the level of the very, very small, realizing at the same time that this also dovetails with how we work and what's going on with us at an experiential and consciousness level, perhaps. At least it is argued that way by many. Uh, so, what I'll do here for a second is just I want to mention and then deepen a little bit on something I talked about last time. Last time we went around this bush, I spent a while explaining about the wave-particle duality and how a very great intellectual mental leap was made by Louis de Broglie, applying what was known about optical waves, light waves, and using some of the insights of Einstein. And he made the leap to think that our reality is composed of elementary units of something that we might call wave particle duality units. Some people use the word QANs. Uh, Elementary particles, when we get all the way down to things with just one piece, they will behave in such a way that it seems like they're obeying the mathematics of waves when we're not messing with them, measuring them, interacting, but they then will turn around and present a particle-like position and energy or other kinds of properties when we interrogate them. And this took quite a while for people to sort out and try to understand and figure out what was going on with that. When is it one way? When is it the other way? What eventually was ascertained is that we cannot separate the wave from the particle. Neither a description is adequate to the full reality that we see. We end up having to use the mathematics of waves to understand what's going on in terms of where they will distribute probabilistically. And yet, when we measure them, grab a hold and know something was right there, then, for that instant at least, in that moment we can get a crisp answer about at least some of the variables involved in these particles, such as position. Neither of these descriptions gives us a full handle on what's going on by itself. We need them both, and yet they seem incompatible, contradictory. Well, in life generally, when we're presented with an either-or choice that seems impossible, seems contradictory, it's interesting to me to note that those extreme collisions tend to melt over time as we learn more, mature more, uh, rise above it. We are now in the process of sort of doing that. There is a strong movement amongst a large number of quantum physicists to find paradigms, find explanations that will allow an easy getting along or meshing, or at least a plausible meshing of this wave and this particle-like nature. And a lot of this centers around something we call the measurement problem. And so put those words in memory, and I'll cycle back to it. So one of the figures that I showed in our talk last time looked like this. And what I was trying to depict there was just a light wave advancing as undifferentiated states of quantum possibility and encountering a barrier. And then the funny looking business over there on this side is what you might expect to see if you were exposing, say, a film plate uh, in profile in terms of where the particles would hit. So I want to amplify that concept a little bit more. I'm going to show you a new picture. Suppose we send wavicles, quantum particles with a wave character associated, down a pipe and encounter a little narrow hole, an orifice. What you'll see at the detector will look like this. This, by the way, I'm using here a lovely book. It's called Quantum Reality by Nick Herbert. And I'd strongly recommend this to anybody who would like to deepen into this area a little bit. This is a pretty old book now. I'm sure that used copies can be had for very little off of Amazon. But the information is very well presented, doesn't go obsolete in any kind of quick time frame. So here's a picture of something called an airy disk. Let's see if I can get a best representation. So you see those concentric circles? So we got a big dark spot in the middle, and then it goes light, and then it goes dark and light. It's kind of like an archery target. Well, this here represents what you get if you, in this particular example, are shooting electron beam down a pipe and hitting a very small orifice. That you can adjust the size of that orifice, and you can also mess with the energy with which the electrons are going down and the intensity of the beam, meaning the flux, the electrons per second. Well, if you get everything just right, you'll see that at your detector. And of course, early detectors for this stuff were photographic plates. So that would be the image that would develop on a photographic plate over time. Now, the interesting thing, the strange thing is that we can explain that pattern very easily using the mathematics of waves, where waves of some material are going through, hitting this orifice, and then spreading out. And that thing that you're seeing there is called a diffraction pattern, and it arises because of edge effects. I spent a while trying to develop a figure where I could show you the edge effects and how you get alternating bands of cancellation and reinforcement, and I gave up. I was not able to get a diagram good enough to really help things more than confusing the issue. So I'll just sort of have to leave that at the level of description. That this interference pattern, or excuse me, diffraction pattern, is observed, it was first observed and described actually in the context of light. If you look at a star through a telescope, that's the pattern you'll see with your eye. And it's because the star is a very distant point source, and it comes in and it encounters the optics of your telescope, which involves a round orifice of a lens or a mirror. That imposes edge effects, just like a tiny orifice does in an electron beam experiment. And what you'll see on your eye is that pattern. As an amateur astronomer, I've spent a lot of my life looking at that exact pattern, where instead of dark rings or dark in the middle, what you're seeing is bright light, because that's what's coming through, and the brightest piece is the piece in the middle. But then you see these beautiful rings, and you can even know if your optics are aligned correctly by whether the rings are perfectly concentric. It's kind of cool. That was observed with light rays back in the like around 1837 or something, by Airy, who is often quoted by astronomers, an English optician and physicist, and I think astronomer. It wasn't done with electrons until much later, but the electron example actually allows more control of variables. And so what people could figure out was that by varying the momentum of the electron, you vary its wavelength. And you need a certain, for the experiment to work with electrons, you need to get to a certain regime where the electron wavelength is approximately on the same size or a little smaller than the orifice you're shooting them through in order to get that projection effect. And that leads me to bring up one of the equations we talked about last time, which was this generalization from photons to quantum particles, where we came up with the equation that said lambda for some particle is equal to Planck's constant over the mass times the velocity. So if you keep the mass constant, say it's electrons, the h was Planck's constant, that strange number we've listed out a few times, 6.63 times 10 to the minus whatever it was. It's a small number, minus 34th Planck units. If you mess with the voltage you're shooting the electrons, you can essentially adjust their wavelength. If you put it through with very high energy, the wavelength is small, because this is an inverse relationship. You can see that the wavelength of the electron, lambda, is inverse to the velocity. So you crank the velocity up, the wavelength shrinks, and the target, the orifice, starts looking big relative to the electrons. In that case, what you'll see from the airy disk measurement is mostly just the dark spot in the middle. As you get the orifice smaller or make the wavelength bigger, that's when you see these beautiful ring patterns. There's an interesting fact is that you can actually observe the light analog of this with your eyes and without a telescope. If you just take a piece of tinfoil and make the tiniest little pinprick as you can in that and hold it up at night and arrange yourself properly, so this is pretty close to your eye, and then look at a distant street light or something, a distant light source, a point source. So you want it to be far enough away that you can't really see the extent of the light. It looks kind of like a distant star, kind of a street light. And get to looking through that little pinhole, and boom, you'll hit a place where you see those rings. Another place where you may have seen these is if you have floaters in your eye. So floaters in your eye are little cells, or at least some of them, not the big blobby ones, but just the small little floaters. Those are cells left over in the fluid in your eye from when you were an infant, actually. And they will have those ring patterns sometimes under certain just perfect circumstances. It's kind of a cool thing to know that we can experience these things ourselves in non-exotic situations. Well, what's happening in terms of how we think about this entity we call a wave function? I'm going to go back just to this picture for a minute. As the light ray or a wave packet, whether it's an electron or a light ray, it comes moving in from the left and encounters a barrier. It's existing in a state of undifferentiated possibilities until it hits the barrier. Then it starts going through in a wave front. And that wave front is describable by an entity in the mathematics of quantum physics that we call the wave function. The wave function is a mathematical entity that looks different depending on the kind of particle and the context that we are investigating. But it contains wave-like properties. And it's spread out. That wave function, all it can tell us is a distribution of possible places that the light ray will be detected or the electron will impact and be detected. It cannot tell us exactly where it's going to hit. It just tells us what the distribution is going to look like. And so with this particular case, the distribution is showing the probability bands of where we would expect to find, and in fact do find, a distribution of hits on the screen. But the hits don't come all at once. They only come individually, piece by piece. Another way we can visualize that experiment would be if we were to take a strip across that bullseye-looking thing, and we could get just an alternating set of bands where there's more hits in the middle, then there's places where there's no hits, and then we get the wings falling off to the side where the hit density becomes less and less. If we were looking at that target in the context of a photographic plate, what we'd be seeing would be the places where a photon or an electron hits and converts a grain of silver halide crystal into a developable piece of silver metal. When you develop a film, what you're doing is you're taking light damaged pieces of silver halide crystal that have become unstable with respect to reduction by the developing fluid, and then turning those into pieces of silver metal that look black, and that's where we get the photographic image. Well, okay, fine. It's kind of understandable in the context of a large number of particles coming all at once. Then you get a populated or a crowded wavefront where the mathematics of the diffraction are easily understood, and the presentation of that bullseye pattern is easy, or this set of stripy things that I'm drawing for you. Another way to do it, a modern way to do it, would be instead of a two-dimensional film plane, we would have an array of a CCD sensor, a charge-coupled device. So you would have an array, maybe 1,000 pixels along the top by 1,000 pixels vertical. So then we'd have 1,000,000 pixels. And what do those pixels do? Well, they're operating on quantum mechanical principles. Each of those pixels is attached to a little amplifier such that if an electron hits that point of sensor, that pixel, it pops an electron out of a low energy electron state into a high energy electron state that then allows for a current to flow or the voltage signal to be captured. Either way can be worked with by electronics. And then you get a readout that says, oh, we got a hit at position blah. Well, if you shoot through a bright beam, you'll get it all at once, that ring pattern. If you turn down the intensity of the electron gun so that there's only, say, one electron dribbling in per second, it might take you a few days to build up the signal, but you still get the same signal, the same pattern. And that's sort of the key mystery of the measurement process in quantum mechanics, because the measurement in that case is, what does the diffraction pattern of this wave function look like? I'm going to measure it. Well, I'm going to measure it by putting up a plate of, say, 1,000,000 CCD pixels that are addressable by row and column number. And you might stop to think, well, if the electrons are entering this apparatus one by one, and yet that means that in any given run, only one of those pixels will get tripped. That's the key mystery right there, is that if you look at it run by run, all you see is a spot on the array that we've constructed for this. But we let the thing run long enough over time, like days. What builds up then is that bullseye pattern. So it means that every time we're doing this experiment, the electron is entering as a wave with a probability distribution dictated by the wave-like part of the quantum wave function. And yet at the moment of detection, that all collapses down to a single point so we can get an answer out of this apparatus, or we are presented with an answer. That has mysteries to it. One of the mysteries is, if you stop to think about it this way, is that this thing has a physical extent in space. That distribution pattern is large enough, and using this kind of apparatus and also other contexts that involve long wavelength photons like microwaves and such, what we're able to show is that the collapse is instantaneous. Somehow this thing is traveling down the apparatus as a state of undifferentiated possibilities, hits this field of detector sites, and bing, it picks one. And it picks it in a way that, as best we can tell, that large macroscopic sized distribution of possibilities collapses to a single point in a way that's instantaneous, and it happens faster even than the speed of light could traverse the full range of possibilities. So something that has spatial extent, which is the field of possibilities, goes bing down to one point instantaneously, as best we can tell so far. Well, that's a little spooky already, yeah, because that starts to violate some of the tenets of relativity, which is that things can't happen faster than the speed of light. Although what really did happen, was the electron existing over that whole range somehow? Part of it over there, part of it over there, and then boom, it's all here. Or is it just information? Could it be a particle that's riding on a wave, so that a wave is somehow guiding the particle, and so it was a particle all along? That's a view of reality that is pushed by David Bohm. The David Bohm pilot wave theory of reality, and his answer to the measurement problem was to invent that scenario. There are other answers to this, what's happening in measurement. The first one was the one that was resorted to by Bohr and Heisenberg. So two of the early and foundational characters in quantum mechanics were Bohr and Heisenberg. And what they settled upon was sort of punt the problem. They would say, don't ask what's happening at the level of the quantum entity and the apparatus interacting. That realm is closed off to us. The only thing quantum mechanics is about is information we get from the mathematics of wave functions. And then what we are able to say later, informationally, about how the wave functions interacted with the apparatus. So we construct conditions on one end of this time sequence, we read results on the other end, and if you ask too many deep, heavy questions about what happened in between apparatus construction and result gathering, you're just wasting time. It's nuts. It's not going to get you anywhere. It has no meaning. Grow up, don't do that. Just get busy constructing apparatuses and collecting information and learning how to make better and better predictions and grow our theory. Well, people didn't really like that. It's very parsimonious, but it's not satisfying. So quantum mechanics evolved along, and this took quite a while, and there was joint efforts between experimentalists and theoreticians. I'll describe one little aspect of this that's quite interesting. I began my reading over the last couple of days, since I mentioned Foundations of Quantum Mechanics in my title. I started relearning them. It's pretty gnarly. I was reading through textbooks I used way back in graduate school, actually. To make a long story very short, I'm going to explain it this way. The way quantum mechanics bootstrapped up into existence were these initial observations that forced a new way of looking at reality on us, like the de Broglie wave-particle duality. People learning how to do more and more subtle experiments on one end, and people doing theory and math on the other end, checking, communicating, going back and forth, people learning which kind of mathematics would allow us to predict what happens under certain circumstances. Then a new experiment gets done that acts differently. Well, okay, theoreticians, here, look at these results. Can you come up with a theoretical model and some new mathematics that lets us make sense of that? And this went back and forth in a very rich, clever, amazing way. And part of the bootstrapping was to flesh out and fully understand operator mathematics. Hermitian operator mathematics ended up being part of the key. Operators, one of the things, okay, Schrodinger equation, in its simplest form. I'm going to show you a boiled down, non-scary version of the math. H operator, that's called a Hamiltonian operator, on the wave function will give you back an energy value times the same wave function. So that's kind of the simplest way I can write for you the Schrodinger equation. We'll do it a little bit more fully next time. That H thing is an operator, and it's doing things when you expand it and put it out in all its full mathematical glory. It's doing things to these wave function expressions that result in discrete values of some property, like energy in that case. So it'll turn out that this system could have an energy spectrum of from low to medium to high, and it happens in steps. That's the quantized part. Well, the Hermitian operator math was developed along with a set of postulates of quantum mechanics. So postulates, it's not exactly, I think, synonymous with axioms, but it's pretty close. Depending if you're reading a chemistry book or a physics book, there's anywhere between 7 and 9 fundamental postulates of quantum mechanics, which are just rules, essentially. It's like if we apply Hermitian operator mathematics, Hermitian is just a word referring to how operators handle imaginary numbers and complex conjugates. Hermitian operator math, working on these wave functions and observing these rules over here, and we've got rules 1 to 6 or 1 to 9, we can make sense of things pretty well. We can explain, we can predict, let's say we can predict and describe reality at a very fine level. I am being a little sloppy there. There's a subtle and important difference between mathematically describing something and explaining it. I used the word explain there a minute ago. I shouldn't, because the difference between describing and explaining is sort of the crux of the measurement problem. Quantum measurements are great at describing what happens when we do the experiment with the apparatus we set up. That doesn't really explain what happened between there and there. And this is the problem. So one explanation was the David Bohm explanation I just explained. Another one was the Bohr-Heisenberg, don't try to explain it. That's kid stuff. Another one, however, was given to us by the famous theoretical mathematician who took up the explanation of the quantum measurement problem. How do we go from wave to particle? His name was John von Neumann. John von Neumann was an Einstein-level brain, and he was already very famous and well-established when he started doing this. And he looked into as deep a level as he could, using what was known about the quantum mechanical math and the postulates. Those postulates evolve, the rules, they evolve as the provisos we have to put on this whole situation so that our mathematics gives us answers that correspond to the reality we see. And so there's this huge bootstrapping thing going on between measured reality, newly erected and fancified mathematics that can describe even more, and it all was coming into business when John von Neumann went into his deep analysis. And he was the kind of guy where he's really thinking hard, the light's kind of dim, and then he comes back up with an answer. Well, he came up with the notion that what was going on with reality were, he called it process one and process two phenomena, where process one phenomena involves wave functions evolving along, doing their thing according to mathematical rules of behavior and time dynamics, then occasionally getting pinched, getting perturbed, and being forced into a situation of collapse. So that going from the distributed wave function to discrete collapse, and then you let them go and they just start evolving again according now to the same or new rules depending on how reversible that transition was. Some measurements involve complete irreversible destruction of the system, some don't. But what he focused in on, he was the first one to say that the key thing that's different, as best as he could figure out, what is special about the measurement process is that something changes irreversibly in the mind of an observer. And most typically, it's the person who built the apparatus. He came down to that as the distinction. And of course, people sort of had to listen, even though they didn't want to. This was not happily received by the physics community, because if you think about one of the explanations of that, it sort of means, well, quantum physicist constructs the apparatus, and he knows the target he's shooting things through, or maybe his experiment involves fooling around with polarized light. Well, he knows how to set the polarizer angles and beam splitters and make this apparatus so that photons are going to go through there and bounce around and hit this filter, hit that filter, you get a beam split. Then we're going to look at when photons hit different places and time correlations. Well, if you take the John von Neumann argument, what it means is the physicist is creating reality. The physicist, by choice of experimental conditions and parameters, is creating the reality that is presented later on the detector, as he reads the detector. And that's kind of attractive, I guess, on one level. There's a certain romantic appeal to that consciousness of an observer would be crucial to this process, crucial to the universe working at the deepest level that we seem to be able to probe in a systematic fashion. But it's also a little disturbing, and it feels fraught. I can understand why people found that to be a kind of a fraught and difficult concept, partly because it's so appealing. When you run across an idea like that is kind of so fantastic and has this romantic appeal of the consciousness of the observer. Hey, I could be an observer. This could be my consciousness in there creating reality. Wow. Well, this gives rise to among some folks, a very enthusiastic uptake of the observer created reality idea. And then there's other people who I can understand quite well and probably identify more with, sitting back thinking, there's probably just something we're missing here. The idea of observers creating the universe, just that's a little hard to hack. Well, that debate is still going on. It's still very alive, and I'm going to be touching on this in different ways over our next meetings. Um, the diversity of interpretations of quantum mechanics that have evolved since the 1920s and maybe early 30s. I've forgotten exactly when von Neumann was doing that explanatory process. It is by no means settled. There are now many, many more interpretations. I looked in Wikipedia at interpretations of quantum mechanics. I think there was like 16 of them. It's change. It's a moving target. Very good, well thought out, interesting interpretations of quantum mechanics, but we still haven't been able to sort this out. The one that I'll be getting to, I keep saying I'm going to get to this because I like it, and then I realize I need to introduce more before I get to it. One of the interpretations of quantum mechanics that I happen to like is this one, and this is the transactional interpretation of quantum mechanics, where you see the kind of wiggly wave functiony hands doing a handshake right there. That's referring to something called the quantum handshake, which is a handshake between what is being called in this case quantum offer waves and confirmation waves, where the offer wave is, say, coming from an emitter like the electron gun. The confirmation wave would be coming backwards in time from the pixel on the detector, saying, "Yeah, I'll offer to accept your, or I'll confirm your offer wave, and maybe we can set up a transaction here and have a quantum event." So that's a little preview of how I'll be getting to this either next time or the one after. Because there's something elegant about it, and it actually is a realist interpretation that allows us to let go of inserting the consciousness of the experimenter into the construction of reality. I'll pick a couple of the other ones and try to go over them next time. I think for now I've probably given you enough, and I hope you're all doing well, and you have a great couple of months until I'm back here with more. Okay. Good night to all of you.